Oh, hi, welcome to part C of chapter 10. This is going to be the last section in chapter 10, Chemical Bonding 1, the Lewis model. In part C, we will cover section 10.8, 10.9, 10.10, and 10.11, the bonding in metals, the electron C model. Without wasting my time, let me just dive into a 10.0 resonance structures and formal charge. What are resonance structures? Structures, these are structures of the same molecule. Same molecule or polyatomic ion, all right? Structures of the same molecule or polyatomic ion having or with same skeletal formula, but different arrangement of electrons. Is this they differ by the position of, all right, the position of electrons. Lewis model localized electrons between atoms that are bonding. Extension of this localization of electrons, there's some degree of the localization of electrons. We call this concept resonance. Resonance. Example is sulfur dioxide, or even in ozone, double bond can be on this end or it can be on this end. There are two resonance structures for ozone. If you look at the skeletal, they differ only by the position of the double bond. You see, they represent resonance structures. When there is more than one Lewis structure possible, they only differ in the position of electrons. We call those resonance structures. Sometimes you may be asked to define or draw the possible resonance structures for a particular molecule or polyatomic ion. Know that the position, you can just vary that. This is not the only example. We can also have sulfur dioxide, which can have a double bond on this side with oxygen on this side too, with an arrow, or either double bond on this side, left or right side. These are resonance structures. You see resonance structures, they vary only by the position. The other is just using here what is meant by resonance structure. This is an hybrid of what comes using ozone as an example. The dotted lines here represent the delocalized electrons on the central oxygen in ozone. Which structure is not the resonance structure of the ion shown here? If you look at the structure, sulfur, all right, or rather nitrogen cannot form more than 3 bonds. It can form 1, it can form 2, it can form 3. Structure B is not a resonance structure because of the possible number of bonds nitrogen can form. From the Lewis structure, dot symbol for nitrogen. If you look at the dot symbol for nitrogen, it has 1, 2, 3. It can form up to 3 bonds, But if you look at B, 1, 2, 3, 4, 4 bonds, it's not possible for that. So correct answer is for this case. How many equivalent resonance structures can be drawn for sulfur dioxide without expanding the octet rule on sulfur? Do this. Sulfur is in group 6, oxygen is in group 6 times 2, 6 times 2. This is 12. We have 18 valence electrons. Remember how to draw the Lewis structure? So if I draw now the skeleton, sulfur is at the center, hooked up to the 2 oxygen, subtract the bonding. So it's 18 minus 4 remain 14. 14 electrons remaining. We satisfy the octet rule on the external atom first before you work on the central atom. Central atom in this case is sulfur. So minus 12 remain 2 electrons remaining. So if I put 2 here, put 2 there, all right, put 2 there. This will be the structure for sulfur dioxide. But sulfur does not satisfy the octet rule. Look, 1, 2, 3. So we can either form a double bond here and get rid of either 2 there. Or we can have oxygen with 8 electrons, sulfur, and then double bond there, oxygen. So there are only two possible equivalent resonance structures. You see this S with an arrow shows that they are equivalent resonance structure. So here, single bond, 6 electrons, sulfur, double bond oxygen, like that, no, only 2 like that. So there are possible resonance structures for sulfur dioxide. This is going back to drawing the Lewis structure for molecule. Otherwise, you cannot, this kind of work, you cannot just memorize. You have to do the work, you have to draw the Lewis structure and move around the double bond, move around the triple bond to see the possible number of resonance structures. Now, let's see formal charge. It's a fictitious. It's just like a number assigned to an atom in a molecule or polyatomic ion, and it is used to determine the most stable resonance structure in for a particular polyatomic ion or an atom. Remember, formal charge Fc. I'm going to be using Fc for formal charge. And here is my equation. F is given by the valence electrons minus non-bonding electrons minus a half bonding electrons. Remember what I mean here is valence electron for an element, for an atom in a molecule. Using the periodic table, you should determine that minus non-bonding minus half bonding. What I mean by that is, let's say, for example, in this resonance structure for sulfur dioxide, if we want to find the formal charge for sulfur, it will be valence electron minus non-bonding electron minus a half bonding electron. So this will be 6. Remember, sulfur is in group 6, so 6 valence electrons minus non-bonding. So if here, I know I forget to put the dot there to make it 8. So non-bonding is 2 minus I have a bonding electron. The bonding electron is 1, 2, 3. Don't count that. This is a bond, this is a bond, this is a bond. So we have 6 times half of 6 is 3. So 6 minus 5 is equals positive 1. This is the formal charge for sulfur to show you how this equation is used. And this positive 1 is just a fictitious number, which is used to determine the total combination for formal charges in a molecule or polyatomic ion is used to determine which one is the most plausible resonance structure for a molecule or polyatomic ion. Remember, valence electrons, look at the group number for main group, minus non-bonding. Non-bonding are the dots on that or sitting on that particular element. Here we have 1, 2, we have 4 electrons, 4 non-bonding electrons, 2 times 2, we have 4 bonding. I have 4 here, that's how you plug in this equation. Sum of all formal charges in a molecule is 0, but if it is a polyatomic ion, it should be equals to the overall charge. Using carbon dioxide, all right, there are 2 possible, possible structures for Lewis structure for carbon dioxide. If you look at the 2 structures here, structure A, structure B, let me just blow up this, structure A and structure B. None of the structures violate any octet rule or duet rule. We don't even have hydrogen here, but oxygen stays satisfied the octet rule, carbon satisfied the octet rule, right? But if we go by the formal charge here, the highest combination here, -1 + 1, this is 0. This is the most plausible, acceptable formal structure or Lewis structure for carbon dioxide. We assign the formal charge to determine if or determine which structure is the most stable. So we'll go with this, but not this. There's nothing wrong with this, but the only formal charge is here tells us that this is the plausible Lewis structure for that. So if I look at these 2 here, one other thing you need to remember about the Lewis structure is the one atom formal charge closest to the 0. So closest to the 0, but we cannot go with this, right? Because of the -2. Now, this I know you can say which one is weak. They are the same, but this one is nitrogen is more electronegative than sulfur, so it tends to have a negative value. We go with this because of the negative. Put negative formal charge on the most electronegative. So we compare nitrogen and sulfur, even though both of them, they have the same combination, this will not be the case. This will not be the case because of the high value, high combination for that. This cannot be the case because we are putting negative on the least electronegative. Remember these 2 bullet points on how to determine the plausible Lewis structure using the formal charge, You should be able to calculate the formal charge. It's pretty straightforward. All you have to do is remember the formula, Here is an example on how to calculate the formal charge. Learning check. What is the formal charge on nitrogen in nitrate ion? This is the nitrate ion. So formal charge is given by, let me just minimize this. You see my whiteboard is given by the valence electrons minus the non-bonding electrons minus a half bonding electrons. So if I plug in this equation for nitrogen, this will be 5. Nitrogen is in group 5 minus 0 because I don't see any dots on any electron on nitrogen. So it's going to be 0 minus a half of the bonding electrons. So here there are two, there are four. So 1, 2, 3, 4, they are a half of 8. So this will be 4, 5 minus 4 equals positive 1. So this is the formal charge. The formal charge for nitrogen in nitrate ion, the correct answer is C. Please see problem number 69, 70, 73, 75. I think this should be 77, not 777, problem number 77. I do apologize for that. Page 440 on this will give you good exercise on how to calculate the formal charge of an element in a molecule or a polyatomic ion. These are just a summary of evaluating resonance structures using the formal charge. You can read on those, pretty straightforward. Please, there are some exception to octet rule when we have odd number of electrons, such as is nitrogen monoxide, free radical, that means they are positive, incomplete, expandable. I know when we were going through the octet rule, I talked about the duet and fulfilling the octet rule ending with 8, but there are some exceptions though. Please be careful. It's not always that an element in a molecule or polyatomic ion should end up with 8 electrons for octet or duet 2 electrons for that. There are some exceptions, and you need to remember the 3 of them. Exception for octet rule, if they are ions or molecules with odd number of electrons, if they are ions or molecules with less octet rule. In this case, boron or aluminum incomplete octet rules, and expanded octet rule, that element on row 3 and below always have expanded octet rule. Look at this ion molecule with more than 8 valence electrons. Why row 3? Because we have the 3D sublevel. Remember, 3D sublevel can take up to a maximum of 10 electrons. So at times you may find the central atom has or will take more than 8 because of the expanded octet rule. This is just a repetition of what I just went through. Bullet number 1 on the octet rule exception, odd number of electrons, such as in nitrogen monoxide, fewer than 8 elements in the second period before carbon can make stable compound with fewer than 8. Boron trifluoride, giving boron field octet rule a negative charge. So you need to look at that. And lastly, we have more than 8. Phosphorus is in row 3. If you look at the 1, 2, 3, 4, 5 times 2, 10 electrons. You can wonder why do we have that? Because it is expandable. 3D sublevel, 3D sublevel. Of the following, dash cannot accommodate more than an octet rule. It's beryllium, it's in row 2. The rest, they have a D sublevel, which can take up to 10 electron transition metals. Which molecule will you expect to be a free radical? In this case, you cannot also just memorize which molecule is a free radical, which one is not, so that you just answer the question in exam or a quiz. You have to do the calculation. How many electrons do you have in order to determine whether it is a free radical? A free radical has odd number of electrons. If I look at A, all right, A adding the number of electrons in A, this will be 4. So A, this will have 10 electrons. B will have 16 electrons, C will have 16 electrons, D will have 13 valence electrons. That's how you determine which one is a free radical. Free radicals are those species with odd number of electrons, odd. That's the only way you can think of. And they are very reactive. They are very reactive. So you have to do the math, see how many valence electrons they are. Which molecule will have an expanded octet? It's B because of phosphorus is in row 3 and below, carbon central atom, nitrogen central atom, second row. So it's problem here is B. Please look at problem number 71, 73, 75, 79 on page 440 on free radical and how to determine the valence electron, see the exception. Just cruising towards the end of the chapter, 10.10 pound energies and bond length, right? You should be able to define the bond energy. Bond energy is the energy required to break the bond. Bond enthalpy, in other words, the amount of energy it takes to break the bond. In a gaseous phase, always positive is endothermic because you are adding in energy to break the chemical bond. You need to know the trend in bond energies. In this case, if you look at the triple bond, double bond, and single bond, I'll say triple bond here is stronger than double bond, which is stronger than the single bond. This is the strength of bond using the lines for triple bond, single bond, and double bond. The trend. You need to know those. You don't need to remember the numerical values for this, but I'm just going to look at the trend on double bond, single bond, and the triple bond, how much you need to bring that. Here are the values if need be. I'll give you this in exam. We're gonna be looking at this later on, right? On how to calculate the enthalpy for reaction. This is where we are going with this, calculating the enthalpy for reaction. The overall enthalpy for change of reaction can be calculated as the sum of enthalpies of change associated with breaking the required bonds in a reactant forming the required bonds in the product. We will use the bond enthalpies to calculate the change in enthalpy for the reaction just the way we did before. So we'll be given this if need be, so that we use to calculate the enthalpy for what? For the reaction. Look at the double bond and the triple bond and the single bond. The triple bond is the strongest, need a lot of energy. And by the way, this is joules per mole, kilojoules per mole for 1 mole. Now, so don't worry about memorizing the enthalpies or bond enthalpies, bond energies. This is the most important. I want you to look at the equation. I'll give you in the exam summation of the, this means summation of the bonds broken in the reactant. These are the reactant which is positive, plus the summation of the bond energies formed in the product. Remember, electron affinity when forming, it is negative. When breaking, it is positive. So the product side should be negative, all negative values. And reactant side, they are all positive values in calculating the enthalpy for reaction. Okay, enthalpy for reaction. So let's see enthalpy for reaction for the formation of bond breaking, estimating the change in. I'll show you an example on that later on. But first, Let's look at the bond length. How do you define the bond length? The distance between the nuclei of bonded atom is called the nuclear. If you look as you go down, the radius get larger as you go down the periodic table. And because of the actual bond, it depends on the other atoms around the bonded, often average bond, similar for that. So bond length increases as you go down the periodic table for two same things. Bone length, if you look at this, triple bond is shorter than double bond, which in turn is shorter than the single bond. In terms of the bond length, you need to know the trend, single bond, triple bond. These are the bond length. Let's see, how do we calculate the enthalpy for reaction for this? Using the enthalpy for reaction given by the summation for changing enthalpy for products plus summation for changing enthalpy for products. Remember, these are negative. So these are negative. And if I want to calculate for this, you ask yourself how many bonds are broken for each one of them. If I look at A, here there are 4 carbon to hydrogen. If you look at carbon, hydrogen, 1, 2, 3, 4. That's why I have 4 here. Plus, because of the summation here, 1 carbon triple bond here. Plus negative. No, not negative. I'm not done yet with the product. I mean, reactant. So I'm done with the first ethylene, first compound here. There are 4 carbon hydrogen bond and carbon to carbon. And then you account for hydrogen. 1 hydrogen Cl. So if I plug in the values here, this will be 4 times 413. You'll be given that 413 carbon hydrogen 413 plus carbon to carbon is 614 plus hydrogen for that one. This is 2,697 kilojoules. This is the product. I mean, reagent for products. One, two, three, four, five. So it's 5 carbon to hydrogen because of what? 5, 1, 2, 3, 4, 5 plus carbon to carbon, 1 carbon to carbon, and then plus carbon to chloride. So here is 5 times 413 plus 348 plus 328. This will be 2,741. And remember, it was negative. It's negative. So for the product, it's negative 2744. So if we plug in with that, negative 224, this will be 2697 minus 224. 2, 6, 9, 7 minus 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 2, 6, 9, 7 27, 44, 27, 44, which is equals to 44, negative 44 kilojoules per mole. You need to. The challenge here is now if you have, if it's not expanded, this is expanded structural formula. Suppose you are given something such as CH4, and you see, you should be translate this to C. That way you'll be able to see how many bonds are broken. Suppose you are given CH3OH, methanol. This will be C3, hydrogen, 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 bonded to O, bonded to hydrogen. So unless you really draw the expanded, you won't be able to see how bonds are broken. I don't expect you to memorize the numbers here. You'll be given in the quiz, in the exam, yours is to really apply this equation, where is the equation? This is the equation I use. And remember, for the product, they are always negative. They are always negative, and that's why I changed these to negative. That's why I changed the product to negative, because they are always negative. And you just plug in that. Just give us the correct answer, which is A. Please practice more on calculating the enthalpy for reaction using the bonds. Now, bond enthalpy and bond length, this is just a repetition on the strength of the bond, that always the triple bond is stronger than the double bond is stronger than the single bond. Which bond has the highest bond dissociation energy? It's the triple bond, which is C. We just looked at that. You need to read more on the bond strength. Problem 85, 86, 87, and 89 on page 439. You should have the answers at the back of the book. Practice with those. Even self-check quiz on chapter 10 will help you master on the strength of dissociation. Lastly, I won't spend time on 11, section 10.11, bonding in metals, the electrons. See, this is just, explanation on what is metallic bond. Remember, metals have low ionization energy, and therefore they lose their valence electron easily. Bonding result in metals, bonding result from attraction of cation for delocalized electrons. Read more on that in the text. And this marks the end of chapter 10. All right, I'll see you again in chapter 11. Thank you.